Hello everyone, this is Chapter 8, number 110, Reassessment number 12. So Part A of the question asks us what is the hoop's angular velocity when it arrives at the bottom of the ramp or the incline. So it gives us a distance of 10 meters, a circumference of 2 meters, and it gives us the time of 10 seconds. We want to figure out first with the number of rotations of the hoop when it reaches the bottom. So we just take the distance divided by the circumference, so we get 5 revolutions. We can use this equation right here. Angular speed equals 5 revolutions over 10 seconds. We'll get 0.5 revolutions per second. We want to convert that to rads per second. So we just take 2 pi, multiply that, we'll get 3.14, which is kind of weird because that is equal to pi, but we'll just use that for now. Alright, so part B asks us what is the angular momentum of the hoop when it reaches the bottom of the incline if its mass is 1.5 kilograms and is concentrated at its rim. So this is actually a several step process here. So we got mass equals 1.5 kilograms. That gives us that. We're going to use this equation right here. Inertia equals m times r squared. R equals the circumference divided by 2 pi r. That's the radius. So yeah, we plug in our numbers. We get 2 meters over 2 pi r, and we'll get, sorry, 2 pi, there's no r. R is right here. We'll get a 0.3183 meters. We'll take that and we'll plug it into our inertia equation we have right here, and come out to be 0.15197 kilograms meters squared. It's our inertia, and we'll use that. These actually come in handy later, but I mean they come in handy now, but we're going to use them more later. So then we go to our angular momentum equation. L equals angular speed times inertia. We got the angular speed in the previous step, and we just got inertia, and it'll come out to be 0.477 kilograms meters squared over seconds. So part C asks us what forces supply the net torque that changes the angular momentum. So I just drew out a little quick diagram right here. We got gravity affecting it, moving it down, and we got the frictional force moving it up. And you know, as the friction force pushes it on that way, it's going to start rolling down the hill because the gravity pulling down. So yeah, it's just the gravitational force and the frictional force to apply the net torque, which then changes the hoop's angular momentum. And finally, hopefully it doesn't cut off right here, but part D asks us what is the magnitude of the force. So we'll use several equations just to really, the torque equals inertia times angular acceleration, and the torque equals force times r. So we can set these equal to each other, and then we'll get F alone. F equals inertia times angular acceleration over r. We could rewrite the angular acceleration as delta angular speed over delta time. So this is the equation, our final equation we want to have. We can plug in all our numbers. 3.14, this is radians per second, get cut off right here. Times our inertia over, we got our radius right here, and then our time. And then it'll come out to be 0.149 newtons for the force that acts on this hoop. Alright, thank you. Hope you guys learned something.